So the motivation is, can we automate the computation of t dt TL tq dot minus TL tq j equals qj. Okay, so this becomes, this calculation becomes very complex, or rather complex, for even simple dynamical systems. E.g. double pendulum. In fact, we will actually derive the equations of a double pendulum. Yeah, so let's take sort of a detour in the sense that we'll do something simple first, and then we just build off to that particular equation. So symbolic derivatives. I'm going to do this by a simple example. Let's say that we want to compute the derivative of x squared plus 2x plus 1. Okay, fairly straightforward. All you do is, if you know the derivative of x squared, that's 2x. The derivative of 2x is 2, and that is our answer. Now, if you want to compute the value of df dx at, let's put x equals 1, then all you do is you sub in the value and you get 4, right? So far, you've done this calculations by hand. But now we have actually can do that using Python. So the way Python will do this is we need a package which people have developed. It's called SymPy. If you don't have it, you might have to install it. You import it just like NumPy. You will import the package. Okay, so I imported it. I need to tell Python that I'm going to create a symbolic variable x. Symbols, this is the syntax. X you put real equals true. The reason why you say real equals true is because by default, it'll assume x as complex. And then you'll see that j's and i's will appear in your derivation, which you don't want. You don't want it to be complex. So next, we'll define f0. This is very straightforward. Once you have defined x as symbolic, x squared plus 2x plus 1. The reason I have this asterisk, so to say, is because this is how you would write it in Python. There's no x raised to it. You have to do x, put the times twice. And then to get df0 dx, okay, which we got by hand calculations, all you say is sy dot diff. So diff is a function in the symbolic package. You just say, you give it the function f0, and then you give it x, and then it will basically compute the derivative. If you want to compute the numeric value, so numeric, then all you do is you say subs, sorry, you should say, sorry, my bad, df t0 dx dot subs x1. So it's saying that take this expression, which I already have, in x substitute x equals 1. Yeah, and I'll show you code which does that. Before we go on and build this up, there is another way of computing the derivative, which is purely by means of numerical differentiation. Here we will use symbolic. Numerical is good when you don't really care about the symbolic expressions. So here we care about symbolic expression because we need the symbolic equations in order to use the integrator, but sometimes you just need the derivative. So you can use you can do a numerical derivative for which you do not need the symbolic package. So numerical derivative. Yeah, so assume that you have a curve f, and you're interested in computing what is the derivative at x0. The definition of derivative is that it's the tangent at that point. So it should be something like this. So one way of doing that is to use the definition of the derivative. Derivative is, say, this point, the so df dx equals the definition of derivative is what's the definition? It's f of, say this is the point x1, so it'll be f of x1 minus f of x0 divided by x1 minus x0. So this is basically using a point in the small neighborhood of x. X1 is close to x0, and then using the definition. So definition is what's like the definition of a derivative? It's the slope. Slope is given by f of x1 minus f of x0, x1 minus x0. So x typically would take x1 to be x0 plus 1e negative 4. Okay, this equation is also known as the forward difference. Forward difference. It's not that accurate, so people come up with better and better ways of estimating the derivative. One simpler expression, a relatively simple expression, which but will give you twice as much accuracy, would be what people call the central difference. So if you have the curve and you're trying to estimate the value at x0, instead of using the point x1 to the right, you use 2 points, one to the left, one to the right. X1, we call this x2, x1. The value here is f2. The value here is f1, let's say. So you would compute df dx as f2 minus f1 divided by x2 minus x1. Okay, this formula is known as central difference. It is more accurate than forward forward difference. So so the only thing you need to choose is x1, x2. So typically you'll choose x1 to be x0 plus 10 raised to negative 4. Then x1 is negative, x0 minus, and x2 is x0 plus 10 raised to negative 4. So that's the user chosen quantity. You cannot go too small on that, like 1e negative 8, because what will happen is there'll be what they call a round off error. So your calculations are only accurate to so many decimal places. So if they're accurate to, let's say, 5 places, and if you do 1e negative 6, then your 6th decimal place is just garbage value, and it will not give you any meaningful derivative. So you want to keep it small enough, but not too small, so you get round off. You can't have a big value. Let's say you cannot put 0.1, because then that violates the definition of a derivative. It's basically the limit, right, as x2 minus x1 goes to 0. So you cannot just have too wide points like this. It doesn't make sense. 10 raised to negative 4. Yeah, that is 10 raised to negative 4. Okay, or you can write it as 1e negative 4, which is also 10 raised to negative 4. Same thing. Okay, now we'll get into more complicated things, but let me show you some code which does this symbolically, and then we'll use the forward difference to verify, central difference to verify that. Okay, what I have here is code which will essentially do the same, essentially transferring what I wrote in the notes. Okay, I'm trying to compute the derivative of x squared plus 2x plus 1, and we know the derivative is 2x plus 2. So I'll run this, and then what I've done here is I have it, the f of x here, x squared plus 2x plus 1. The derivative df dx is 2x plus 2. How did we get this? It's right here. It's just printed, but this is how it was computed, diff. If you want to compute the value of df dx at 1, then you do subs x xval. Here xval is 1, and so it actually went a step further and computed the derivative is 4, right? 2x, when you put x equals 1, you get 4. So that's how you would do it in Python using symbolic toolbox. Here is how to do the same thing using I believe I've done both central, and I've done forward and central difference. So here I have defined f0 with the symbolic toolbox, but you really don't need it. If you just can define like a function. So if you input x, it gives you f0. So here I want to compute the derivative at 1, like before. I perturb. So instead of using 10 raised to negative 4, I use 10 raised to negative 5. And I compute f0, f1, f2, the same things which I wrote down on paper, and then forward difference. f2 is my value, which is perturbed by a positive number, and then central difference, which is f2, f1, the same thing I wrote down. So if you run this, you see that for this function, the forward difference gives 4.0001 and 4.000. So you can see that this particular approximation is accurate to what? 1, 2, 3, 5 decimal places. So you can see that 1 in the 5th decimal place, that should be 0, right? So it's accurate only to 5 places. But this one is more accurate. It's actually accurate all the way till here. I don't know, maybe 8 or 10 places. So you get much more accuracy with central difference. Now, this will be even more visible if you try to take a more complex expression, like take e raised to x sin x, take something very complicated, and you'll see that central difference will always win over forward difference. But forward, some point of time, central difference also will give you, may give you poor performance, because after all, it's just an approximation of the derivative. Okay, let's get to chain rule. Okay, so we're getting to doing more complicated things. Let's talk a little bit about chain rule. This is sort of a revision of what you've done before. Okay, if we have a function x, so far we've seen just that, right? If f1 is a function of x, compute df dx. Okay, so that's the complete derivative, and it's easy to do that. But what if x was a function of t? So example would be the trajectory of a car. That's x and y, but then x again is a function of time because the trajectory is a function of time. So the question is compute df1 dt. Okay, so the way I like to think about this is the following. F1 is a function of x, and x is a function of t. So if you want to compute the derivative of f1 with respect to dt, what you need to do is you need to go through x to t. So then the chain rule is what is the way you do it, df dx dx dt. And then, of course, you can write it down, whatever that formula is. So here's an example. If I gave you f1 sine of x of t, if you are asked to compute df dt, using this chain rule, we have d sine x dx. Okay, here you treat x the way it is. You don't really look at t. And then the second part is dx dt. So the derivative of sine x is cosine x. This would be cosine x of t. And then dx dt would be dx dt. So x dot. Okay, I just have a notation for that. So x dot is dx dt. So that would be the answer. Okay, so far so good. This is probably the simplest case of applying the chain rule. Now let's make it slightly harder. Let's deal with two variables where f1 is a function of not just one variable, but two variables. So if f2 is a function of x of t, we had that. But what if it's also a function of x dot of t? Then compute df2. So it's a function of two variables, position and velocity. Yes, so this is how you would proceed. I like to again write it in this fashion. F2 is a function of x and x dot, right, as it is, but both these are functions of t. So in order to compute df2 dt, I need to do the same chain rule, but for both variables. So here's the first one. I go from f2 to x to t. Right? I did this in the previous question, which is only a function of x. So that would be df2 dx dx dt. Then I go again with the other variable. So go from f2 to x dot and then to t. That would be plus df, treat x like x dot, so it will be x dot tx dot tt. And of course, once you do it for 2, it's straightforward to go for 3, 4, how many ever you want. So here's an example. F2 is x of t times x dot of t. So position times velocity. So df2 dt is, let's do the first part. So it'll be dx. We just write it this way. Yeah, I just want to write the whole thing down first before I start doing the calculation. This should be 2. df2 dx dt df2 dx dot dt. Okay. So the first part, just write down f2 the way it is. So it's x times x dot dx dt plus dx dot x times x dot dx dot dt. Okay, now is the time when we do the derivative. Since the first one is taking the derivative with respect to x, you treat x dot as a constant. So the derivative of a constant x dot times x is going to be x dot. And then dx dt is also x dot. So it'll be x dot. Let me just write it down here. It's clear in the notes. And then when I do the second part, I need to take the derivative with respect to x dot, which means I treat x as a constant. So that will be x times tx as an error here. This should be, oh, this is fine. Sorry, my bad. Tx. Okay, so to finish this, this thing here, dx dt is nothing but x dot. So it's x dot square plus the rate of change of velocity. So dx dot dt is nothing but acceleration. So x times x double dot. Okay, so what the reason why we did all these things is we are trying to now get to deriving the equations using a computer program. So let's do this for the Euler-Lagrange equations. That is derived by using symbolic package. Back to okay, let's look at specifically the projectile. Okay, so we're going to sort of try to extract out a sort of an algorithm or code which we can just use it for just any problem, and not just the projectile. Okay, so I'll have like and you see that I'll have code which you can then copy paste for any system you're deriving, and it'll give you the equations. You don't have to really do this, and it's only true for this particular equations. Okay, so we saw that L is half m x dot square plus y dot square minus mgy. Okay, where qj was x and y, capital Qj was f dx, f dy, and there was some formula for this which I won't write here. Okay, so what we need to do here is just like f, we looked at f or f2 in the previous part, and we use the chain rule to compute the derivative. Here we are looking at L, and so we better try to understand how L is related to the independent variables. So here L is a function of x dot, y dot, and y, right? But in a generic case, it could also be a function of x. So x, y, x dot, y dot. Okay, and those things are clearly a function of time. So note that we are trying to find the derivative with respect to x and y. So we have TL tx dot, which is this part. Okay, so when we take the derivative of L with respect to x dot, it will just be what it is. There's no chain rule involved. Why there's no chain rule? Because we are not trying to compute the derivative of L with respect to time, right? And if you saw the previous one where we talked about the chain rule, when we were interested in computing f2 with respect to time. So it's more simpler than that. So you just have to take whatever L is, just take the derivative with respect to x dot, and symbolic package will let you do that. All you have to do is say diff with respect to x dot. So this part is easy. This first part. Let's look at this. Shouldn't be a Q. Let me correct that. This is just QJ. If you look at the second part, the part here, DL dq, q is x, then that is also straightforward. There's no chain rule because, again, it's not a function of time. The place where you'll have a chain rule is only in this part, the first part, once you compute dl dq dot. Okay, so I'll just write that formula. So we need to use chain rule for d dt of dl dx dot. So just to make our life easy, I'm just going to create a notation for this. Let's call this Lx dot. So you've computed the derivative and stored it as Lx dot. Now let's go with the chain rule. So I need to go from L to X, then to T. So dl dx, this will be x dot dx dt. So next I need to go from L to Y to T. So that would be plus dl x dot dy dt. Then I go, I got erased. Then let's use blue for L to X dot to T. Then there's one more left. L to Y dot to T. Y dot dy dot dt.
That's a subscript text out, right?
Yes, it's a subscript like this. just to make it easy to notate dl dx dot. So this is where the chain rule comes. Only in one expression. And so we just keep it that way. Once you have identified L is a function of the independent variables x, y, and its rate, we just use that. Yeah, I'm going to show you a code which essentially generates the equations of motion for the projectile. Something which we did by hand will be done by code. And then once you have the equations, you can then put them in the simulation and make an animation. I have 2 minutes. Here are the equations I derived last class. Summary. These are the equations, and I'm trying to get the same equations using symbolics. Okay, so x, y, x dot, y dot, x double dot, y double dot. Now I also need to define the constants in the problem: mass, drag constant, gravity. So I'm just trying to follow the same recipe I had, Euler-Lagrange. I need to specify position. That's really need not be done here. You can skip that. It's already been done in the symbolic ones. You'll need this later on in the double pendulum. I defined kinetic and potential energy, T and V, specify the Lagrangian. And then I go to compute the drag force, which is a formula from the notes. Then this is where the equations come in. I need to use Euler-Lagrange. So L, as I said, is a function of x, y, x dot, y dot. So this part does not have the chain rule. So I just have it as it is. This part, the third part, doesn't have chain rule. This is the part which has the chain rule. This is the same formula, the 4 things I wrote down in the notes. This is done for x, but I need to do the same thing for y. So that's done here. And then once I press, just say solve, it gives me the solution for x double dot. Okay, now that is that when I run this, it'll produce the code, but I actually made it much simpler. This code here, what you see here, sort of generalizes it in the sense that you don't need to touch anything. You only need to specify these things in your code. Once you specify it, I would just copy paste the lines below it into any problem, and it will give you the solution. That way, I really don't need to write dl dy dot ddt dl dy dot. That doesn't really appear here, but it's done by this for loop. So you don't have to think too much about the for loop, how it is generated. If you're interested, you're more than welcome, but it basically does all the calculations for you. So if I run this, this is the equations of motion. Method 1, this was like actually writing the formula as I have it there. X double dot equals minus c, oh my God. X double dot equals minus c x dot, this is the drag force, divided by m. And for y double dot, it will be drag force divided minus g, right? And the same thing, exactly the same thing comes if you use the other method, method 2. Okay. So I'll post this.